So hello everyone. Now, last week we had an introduction, a very comprehensive one. We have covered MATLAB, the basics, the control system toolbox, and some of the symbolic toolbox. This week we will be speeding up a little bit, hopefully, but we will still examine some basic concepts in control that we should maybe probably readdress. And we will be talking about the symbolic toolbox and the control system toolbox today again. And from the upcoming weeks, I'll say we would be more focused on the control part of things. Now, first of all, we have a very basic tool that's called the root locus plot, which we will use often. Therefore, we will be covering that part. We will recreate the root locus plot. And the next thing would be the Bode graph, which is a Bode plot, which is also, again, used a lot in control system design. And we will also look at the impulse step and ramp responses of a transfer function and how we can easily simulate them using the control system toolbox. Now, let's head directly to the tasks of today. First of all, let's try to plot the root locus of a certain symbolic expression. So in order to do that, let's just look at a basic root locus plot. So let me just create a transfer function, hopefully an exciting one. 1, 2, 1, maybe times another transfer function 1 and 3. So there we go. Now, if you might know, we use the rlocus plot, the command rlocus, and we're basically there. So let's call run 1 here. And this plot here appears. Now, do you remember what the root locus plot actually shows us? Because it is quite important to know what it actually does in order to use it. Does anyone have an idea what this plot tells me at the moment? When I look at this, what can I conclude about the system? So any ideas? Türkçe'de sorabilirsiniz arkadaşlar. Sonrasında çeviri yaparım. Kök eğrisine baktığımız zaman ne anlamalıyız?
Bizim tasarım bölgelerimizi belirtiyor aslında. Kutupları.
Tasarım bölgesi. Şimdi ne tasarlıyoruz burada aslında? Ben sadece sistemi aldım ve kök eğrisi çizdirdim. Ne tasarlıyorum şu an?
Ona göre hani o köklerin doğru yerde manipüle edecek bölgeleri aslında belirlememizi büyük bir ipucu sağlıyor diyebilirim.
Tamam. Neyin kökleri?
Kapalı çevrim transfer fonksiyonu.
Kapalı çevrim transfer fonksiyonu. Ben şu an bir transfer fonksiyonu kullandım. İşte nedir o transfer fonksiyonu? Bu. Hatta şurada da görebiliriz. GS bu. Şimdi bu o zaman açık çevrim oluyor. Kapalı çevrim nedir? Şu an bu kök eğrisiyle. Aslında dersimizin adını çok iyi taşıyan bir eğri bu kök eğrisi. Çünkü kontrolör tasarlatıyor bize. Değil mi? Now, this plot actually helps us in designing a controller. And we therefore also have a feedback loop. So let me just show you what I mean by that. So we have an input here. And we'll also have a summation point here, a certain controller, and then a certain system. And we'll have a feedback loop, which is also arguably useful for some reason. Now, we actually have the error signal here. And then the controller generates some control signal, and then the system has an output. Here we have actually a minus sign. So here's a minus sign. So R minus Y gives us E. So this is a closed loop feedback structure, unit feedback structure. And well, we have the actual system, GS. But for some reason, we're not really happy with this system because we need to place it in a feedback loop in order to change its behavior, in order to alter its behavior using a dynamic or static structure called FS. So we have something called FS, which is the controller, and we have GS and this unit feedback loop. So why are we not happy with GS? Well, probably it has a certain step response, for example, and we want to change how the step response actually acts. Or it could be any other input response and output response, this input-output relation. And the behavior there can be something mathematical, can be something else. In that case, we're not really happy with it and we want to change it. This whole course will be about this. So we will try to come up with structures and designs that will ultimately just change how things behave. Here in this case, we have a certain GS, and I can already tell you that if I apply step to GS, I'll get something that will not track its input. And the reason why I say that is because we have this final value theorem where I can just plug in s equals 0, or in other words, multiply with s and the step function 1 divided by s, and then take the limits where s tends to 0. So it's kind of plugging s into 0 because they cancel each other out. I can see that it has a static gain. So eventually the gain of the system is 1 divided by 3. So it's a third. So therefore, if I input something, 1 unit, the output will be 1/3. So if the input is 3, the output will be 1 unit. Now, I say unit, but for an open loop system, most of the time, this is not actually the same measurement. So it's not going to be the same unit here. I say most of the time it could be the case, but it will not likely be like that because most of the systems have different inputs, different type of inputs, and different type of outputs. Let's examine a car, for example. You have the gas pedal, which is probably just something in terms of angle because you will press it in an angle, and your output is velocity. So we have a car here. So the output of that would be velocity. And therefore, the more you press the gas pedal, the speedier you will go, but it's not really that. It's basically the relation will be modeled with GS. And in this case, they don't share the units because they are not the same physical quantities. Therefore, there will be a transformation in that most of the time. Here, we will have this unit feedback, and our reference will be the same unit as the output y, because we want to alter or change the behavior of the car in such a way that we can give it a reference velocity, and the output should have eventually the same velocity as the input. So this is called reference tracking. So we will provide a reference. The system should track that. So this is basically the first aim in control system design that we focus on in this course. And here we have a certain ratio to it. And you might think that if you want to go with a certain, let's say, speed or velocity, then you can just go ahead and calculate this using the relation here or the model itself. And actually, you would be correct in some sense because you would be able to do it under certain circumstances. Now, there's this most basic controller. I'm going to talk about this relationship in the upcoming lessons probably. But let's say we have this car and we want to provide it a reference for its velocity, and our car should be at that velocity. So it's not possible to directly do it here but we have something called open loop structure or open loop strategy where we try to do that or try to replicate that. So here, we don't really look for the velocity of the car. We don't really know what its velocity is, but based on the model itself, what I can do, for example, is I can just give it like 3 times the input that I actually want to give and apply it to the system and hope that eventually I'll get to that speed. Now this works, but it's not the best solution. So the controller would be fs equals 3, and then we would have this transfer function, and we would apply step to it. We can actually do that. Let me show you. So step, gs times 3 times gs. Let's make that a blue color. Let's have gs, black, and see what happens. So there we go. Now we still have this root locus, which I'm going to focus on in a minute. But here you can see they behave differently. Now, if I have a certain input of 1, I can immediately see that it settles down to a third. But if I have an open loop control strategy, what I can do is I can say, okay, we need an amplification. Even though you provide me 1 unit of input, I will have a third of it. So if I triple it, the output should be exactly at that point. So therefore, let's multiply it with 3. So this is an open loop strategy. But if there's, for example, wind, if there are model errors, if it's not really a third, if there are certain other stuff that is not really taken into account at this point, then your open loop control strategy, since it doesn't measure the output, will not be able to compensate because it doesn't know that it should compensate, first of all. So you need measurement in order to detect these types of changes in output or modeling errors or whatever. So therefore, we need to measure the output, take it into consideration, and it is all possible with this basic structure here. This is exactly that. This is taking a measurement from the output, looks at the input, looks at the difference of the input and output, or the reference input and the output, and sees if and looks if there is an error. If that's the case, then you are basing your control input or the system input on that. So what it really translates into is that you will change your gas pedal angle, for example. If your speed is low, you will press it a little more, you will increase your input, reference input, etc., etc. So this is the control strategy here. And root locus focuses on the most basic structure for FS, which is just basically static controller. So by static, I mean it's just a coefficient. So we are looking for the ideal coefficient that can be used here, which is basically the relation between the error and the control input or the system input. So we're looking for a connection between the velocity reference and velocity of the car, the difference of that, and the gas pedal angle. So we try to come up with a ideal coefficient for Fs so that it works better in closed loop, or it works at all. Now, interesting fact is that you need to be careful with this coefficient here, but you don't really have to be careful about this one in the open loop structure. The reason behind that is if you choose a bad coefficient in some sense, you won't mess with the system stability because, as you might know already, the poles of the transfer function actually determine the stability of the overall system, overall transfer function. Now, if you look at the poles, a coefficient coming from here in the open loop strategy does not really affect the poles of the system. It doesn't change the poles of the system. It just changes its gain. Therefore, it will never have an effect of its stability. Whereas here, as we'll see as we progress in this course, this has an effect on the poles. Therefore, we have to be careful about our choice of the coefficient here. So there's a big difference in open loop and closed loop control strategy. Now, let's assume that we are looking for the static coefficient because it can have some dynamic parts in it. It could have an integrator, for example, or a derivative element in it, but it doesn't really have that. We have none of that. We just have a coefficient, and we want to determine what happens to the system in the closed loop, because that's our desired scenario, if we change this gain and how we change this gain. So therefore, the root locus can be used for that. Now, for that same reason, if you're considering basically the root locus plot, what you do is you just place a k because it's coefficient, so let's call it k. Now, we can calculate the resulting closed loop transfer function, and that's going to be one of our steps, because we need to determine what the closed loop transfer function looks like, and then the root locus basically just changes gain over a certain interval and then calculates the closed loop poles. Now you can see that we have a third order system in the open loop, and this coefficient does not really change it because we don't really add any dynamic stuff to it. So the order remains the same. And we see that we are seeing 3 different branches. And if you look closely, we have 2 poles at -1 and then 1 at -3. Therefore, they start at those locations. And as k increases, they depart from that point on these branches here, whereas the third pole just goes to the left. So this is basically telling us that, yeah, what does it really tell us? If you look at this, and if you, well, and at the end of this semester, you would be more informative about this. You would be able to make some comments, but let me give you the comments from the beginning. Now, I can see that the 2 poles will get closer to the j omega axis. And the closer it is, the slower the system becomes. So for this system, if I have a certain k and increase that k, the system will become slower. The third pole is going to the left, which should be a fast mode of it, or a pole, but it will lose its effect because it's going far away, and these are the dominant ones. So therefore, these 2 poles here will determine the behavior of the system more and more. They become closer to the j omega axis, and at some point, we will cross the j omega axis, and it will become not stable, so unstable. This stability problem is an issue that needs to be taken care of if you are using the feedback loop. So in open loop, it doesn't really matter, but here the poles change their locations. So the gain versus poles plot is called the root locus plot, and the root is basically the pole here, so it makes kind of sense. Now, how can we regenerate this plot on our own? It's more based on this, and we will use the symbolic toolbox. So therefore, let's define our exact same system using the symbolic toolbox here. Let's get rid of that. Let's get rid of this. This might stay. So how do we define it? Well, we use sims s, and I'm just going to take this here, divided by, then parentheses, there we go, times s. This is our system. Now, in order to be able to distinguish the symbolic toolbox from control system toolbox, what I do is I append s if it's in symbolic, just one extra s here. So if you see GSS, FSS, or something SS, it means that it will be in the symbolic toolbox. It's the definition based on the symbolic toolbox, whereas the control system toolbox has just one s because I need to define it in both domains most of the time. So that's kind of a rule of thumb. So yeah. Now we have GSS, so we need this coefficient, sims k. And by the way, if you define a certain coefficient, and if you're sure that that should be a real number. It's not a complex number because S is a complex number. It's on the it has the sigma part and j omega part. So yeah, therefore, if you know that k will always remain a real number, you can append this keyword here. So MATLAB will also assume that this is a real number. If you don't provide anything, it will look for the most general solution in the complex domain, but here we can restrict it to the real domain. Now, once we have done that, the only thing that is left is to calculate a closed loop transfer function, and that's kind of easy. We have k times GSS divided by 1 plus k times GSS. Now, of course, if you look at this, it'll look a little bit ugly here. As you can see, what you might want to do is you might want to simplify it in order to get rid of these extra steps because, well, I can also tell you that this is the closed loop, but it didn't carry out the operation in order to end up with this fraction here, which makes more sense. Now, we have the characteristic polynomial here, which is the denominator of a certain system. And we can take the num_den, numerator denominator, it returns two values, num_den. And I'm more interested in the denominator because that will be my main focus. The roots of this should always be stable for certain k values. And I should come up with poles that kind of match my desired behavior. So it's not really easy to understand this relation because you're dealing with behavior, let's say settling time, overshoot, and stuff like that for step response or transient response of a system. These might mean something to you. You might want to have higher settling time values, lower settling time values, certain overshoot values. That might be the desired values. On the other hand, you will have poles, and you try to decide where to place the poles accordingly. So it's not really a direct connection there. There's no direct connection there. But throughout time, you will see that you kind of become accommodated to it. So it will make more sense, but it's not really easy. Still, we have some powerful tools. One of them is root locus. Now, what we might want to do here is we might want to plug in some values for k and then look for the roots of this polynomial. And once we've done that, and if we combine all the roots and k values on a single plot, that would be the root locus itself. So we can do that by, first of all, taking the coefficients here. So if you remember from last week, we use the symbolic variable that is s in this case. We want to look at polynomials in terms of s. And we provided the all keyword here. So it will fill out the blanks, the missing terms here with 0. And it will have the correct order since it has a special meaning for us. In order to be able to reconstruct the polynomial, the order of the coefficients makes the difference here. So yeah, if you mess it up, it will become k plus 3 s cubed plus 7s squared plus 5s plus 1, which is not the original polynomial. So therefore, it should be always with descending power order in order to not mess up stuff. So now what we can do is we can go ahead and substitute values to it. So for example, in order to have a starting point, I want to substitute k equals 0 here. So let's do that. You can see we have plugged in k equals 0. Now I can convert it into double. This is still not double. So let's convert it into double. You will see the difference here. You see that the output of the symbolic toolbox and the actual MATLAB array output are not really the same. So yeah. Now I can use the roots command here in order to get the roots. There we go. -1, -1, -3, which are the open loop poles, of course. Now, if I change the value of this, I'll see that, for example, it started out with 3. Now it became minus 3.2. And at this point, they were coinciding here, but now they became a complex pair. So, and that was also obvious on the plot, because from now on they are complex pairs. So, and they are moving towards the j omega axis. The real part of them will decrease over time. So let's see that effect too. There we go. It was 0.89, now it's 0.75. And the third pole at minus 3 goes far and far away from these two from this pole pair. So now what I can do is I can decide on a certain k vector. Let's start out with 0.1 with 0.1 increment up to, let's say, 0.2. And I have placed it in a for loop. Now what I can do is I can say that these are the poles. By the way, I need to look for kvec here. If you remember, this was more of a for each loop, so kvec, or maybe you're calling it kval in this case, k-value, makes more sense. Now here, I can just go ahead and plot them. And since I'm plotting the poles, and since they might be complex numbers, the x-axis on the S domain is the real part of complex numbers, and the y-axis is the j omega axis, also the imaginary part of these complex numbers. So what I'll do is I will give the plot function first the x-axis and then the y-axis, therefore the real value of these poles and the imaginary values of these poles. So therefore I can go ahead and do real C poles. It will take the real parts of the poles, by the way, of the poles, and the imaginary part of poles, and I can go ahead and plot it. Now, before I do that, I'll open up a new figure and CLF, clear the figure, hold on in order to be able to plot on top of each other, since I'm using a for loop here, and maybe grid on, but it's not really that necessary at this point. So let's plot this and see what the result is going to be. So if you call close all, pay attention to this part on the taskbar, you'll see they vanish, they are gone. I've closed all the figures. Now if I run this, I'll see that they will reappear here. And we have this interesting plot here. Now, if we look closer, we will see that at a certain instant, we will have these coordinates. Now, these are actually the real parts, these are the imaginary parts, but the problem is that we have kind of 3 x coordinates and 3 y coordinates. So what the plot does, it connects these locations. Like, for example, minus 3, 0 will be connected with minus 0.97 and 0.31. And then also with minus 97 and minus 0.31. So this is kind of the thing that is plotted here. And if I want to correct this behavior, I'll give it just a marker. Now, plot usually plots lines. So therefore, if we want to just place like crosses on certain locations, you have to give it a marker. And then, since you didn't provide any type of line, it'll convert it into dots or crosses in this case. Now, of course, we need to increase some visual things here. For example, the line width. If we increase that a little bit, we'll see that it will hopefully become a little bit more visible. But we can see that we are heading to the right direction. Of course, I'm keeping the vector under consideration here as small as possible if I'm just building the code for the first time, or if I'm writing it from scratch. Once I see that it works, I can go ahead and increase it up to a certain value to see the effect here. it's easier to debug with those vectors. So you can see it kind of resembles the path or the trajectory of the root locus. But of course, if you zoom in, it's not a real root locus. You can go ahead and do it, but is it really that important? I would doubt that. What you can do is you can store all these values in vectors and then call just one plot on them so that they will give basically the effect of a line. And in order to do that, let's see what the poles here looks like. So it will have 3 rows because it's a third order system. So each row will be used for each pole of the system, but each column will correspond to a different k value. So what we can do is, in order to show you just the idea here, what we can do is we can come up with a matrix for the poles, and it will have 3 rows and as many columns as the k vector will have elements. So k vec equals this here. So it'll take the length. Then we will have poles. Let me just shrink this again back to 0.2. And once we have done that, we'll just go through each k vector element. The k value will be the ith element of k vec. So I'm basically using the for loop now, not the for each loop. I'm looping through each element and taking the element for a certain cycle, plug it in, get the values. Now, instead of plotting them, let me remove that. What I will do is I will place it to the according position. Now, I will take all the 3 rows, but the ith column, because each column corresponds to the element of this k vec here. So I'm going to stack them into a matrix. So we'll see the effect now. So poles, you can see this is k vec first element, k vec second element, and it will go on like that. And I will then draw a line between these two and all the other ones on the same row. So I will just plot lines based on rows. So that will get rid of that. So let's see. So you can see that -3 has ended up being at -4, whereas the other ones are here. So if I go ahead now and plot them using yeah, so the first row, all the columns, no marker because it's a line, and let's let MATLAB draw it. There we go, we have a straight line. It starts at -3 and stops at somewhere here. Now, if I add all the others, and if I want to be generic as possible, what I can do is I can just say 1 up to 3, for example, and it will do it automatically. So the ith row, there we go. Of course, you can also determine the amount of poles based on this here. You can get the order of the system and then make it even more generic, but I'm not going to use or bother with that. So just change that. And there we go. Now we have a root locus plot. The only thing missing here, by the way, is the open loop positions. We can also do that. So since if we plug in k vec equals 0 here, I can go ahead and do something like this. So once we're done with that, I'm just going to go and take the first, actually the ith first one, the ith and first one, and place a marker with a certain color. And I guess this should be it then now. there we go. We have recreated the root locus plot. Now, the important thing to remember here is that, of course, even though these are lines, these are actually points really finely gridded, and therefore they look like lines. But there's also a theorem that the path of roots are continuous. So if the coefficients do change continuously, the poles will also move continuously on a continuous path, at least. So therefore, these are the lines. So if we increase k, we see that the system has a certain behavior. Now, looking at this, we can go ahead and plot step responses, choose a certain one of them, and then use that k value. But it seems like it's not really wise to increase the k value here, because it will become more oscillatory, because the zeta value, we will talk about this all the time, but it can be seen that the zeta value, if you know what zeta is decreasing, so overshoot will become larger and larger, etc., etc. Now, the root locus plot is basically done. I wanted to remind you that you can use the symbolic toolbox, use this k here, take it to or calculate the closed loop transfer function, plug in certain k values, and look what the root look like. So this is part one. And we can also recreate the Bode plot using the symbolic toolbox. Now, let me remind you of the Bode plot, what it really was. So let's again take this system for some reason, and let's call the Bode command on this. So that's basically it. So there we go. Now, this is a frequency domain plot, and it's again telling something about the system here. So the root locus did give us an idea about the unit feedback with a static controller or static coefficient. So we were trying to choose a certain k value. But most of the time, the root locus is used for step response manipulation. Therefore, it's more of a transient design tool. Here in this case, the Bode plot is a steady state plot. So it's basically a steady state plot. It gives an idea about that. But it is also important to remember that we are basically dealing with a system. And instead of having just the step input as an input, we generalize it and apply a sine wave to it. Now, let's assume that we have a unit gain and unit phase sine wave. So just the plain sine wave. The only thing that we will change is this omega value, which is basically 2 pi times f times t. So we're kind of changing the frequency of the sine wave. We're increasing it from a certain point or decrease it. And we'll observe the output of this system here. Now, since this is basically a linear time invariant transfer function, we will be dealing with linear transfer functions and time invariant transfer functions. Therefore, if you apply a sine wave to it, eventually what you will get in the output is another sine wave. But the difference will be in gain and phase. So, of course, we cannot say that the gain will be the same. If the system has one gain, or gain equal to 1, then this would be the case, but it will change with the gain of the system. So let me, by the way, change it back to omega. So yeah, therefore we don't know what the gain is. So gain, and then here the phase will also change, but we will still have sine waves. Now, it is important because all the periodic and non-periodic signals in nature can be, to some correctness and some level, reconstructed or decomposed into sine waves or sums of sine waves. So therefore, analyzing the system in terms of frequency and sine waves makes quite sense if you think about it. Now here, we can do the same step. We can get the same result as we have here by using the symbolic toolbox. Let me take the definition here back. So there we go. Now instead of this, we will have basically this here. So how can we get this sine input, sine output thing? Well, what we can do is we can first of all plug in s equals j omega. And this step is most of the time not really paid attention to, because this is actually a change of transformation. Now we take the Laplace transform of signals and we ratio it in order to get a transfer function. But basically, we have input-output relation, and we take the inverse Laplace transform in order to fall back to the time domain. So yeah, and the inverse Laplace of this is obviously going to be something else. But what I really mean by this is that we have the Laplace transform of the output in terms of input times the transfer function. And well, if we plug in s equals j omega, the integral that we use for Laplace transform and inverse Laplace transform will become Fourier transform and inverse Fourier transform. So this is quite important and amazing, if you ask me, because we can transition into the Fourier domain somehow. Of course, it's not exactly the discrete Fourier or fast Fourier domain that you might expect, but it's still the Fourier domain because it is the integral. It is the transformation integral. So therefore, if we plug in s equals j omega, we have this nice omega dependent fraction that will give us basically the gain and phase data. Let me show you how. Now, let's define g omega, because it will be omega dependent. Substitute GSS s equals 1i times omega. Now, at this point, it will look like this, which will not make much sense. As you can see, we have this kind of thing here. Now, the trick is to convert it into polar coordinates, because you can see that it is in Cartesian coordinates. You will have a imaginary part and a real part, but that's not what we're looking for. If we take the real part and the imaginary part of g omega, take the squares, sum them, and take the square root of the sum, you'll get the absolute value, or the gain, in other words. If we look for the angle value of this, we will get the phase. So therefore, we can get the gain and phase data directly from g omega. If we simplify, I'm curious if it is going to show it like that. So if we say pretty, let's see. Well, it didn't work out that like I would have expected it, but if you multiply with 1 minus omega I squared and then 3 minus omega I, then you'll be able to separate the imaginary and real parts, etc. So maybe real g omega and imaginary g omega will give us that. Yeah, it did probably give us that, but it's not really easy to read. No problem. We can just take the square of that plus that, and then the square of the imaginary part. take the square root. See if it's working. Yeah, it becomes a bit complicated, but you get the idea. But if you're lazy like me, you can also use the abs on it, abs value, absolute value here. So it should be the same basically, but it has even a better result in terms of readability. Now that's the absolute value. We can also look for the A10 of the imaginary part of g omega divided by the real part of g omega. So this should give us basically this. But if we do it symbolically, we will get stuck because, yeah, we see just omegas and a bunch of terms here, but doesn't really help out. What we can do is we can give certain frequencies to omega. So plug in some frequency values for omega and see what it looks like. That would make more sense. So let's have an omega vector, 0.1, 0.1, let's say 0.2. And let's substitute omega val, let's say omega val. There we go. And I should be equal to 1. So now if we do the same to this one here, there we go. Now we get some numbers finally, but of course we might want to turn them into double values in order to be able to read them better. There we go. 0.3298 and minus 0.2327. Now, what does this mean? Well, this is the gain, so it will reduce down to 0.32 instead of 1. But this is kind of interesting because now this is actually in radians, as far as I remember. So you can use A10D in order to convert it into degrees. Now it's minus 13 degrees. So this means that if we apply a sine wave, so sine 0.1 times t, omega t, the output will look like 0.3298 times sine 0.1 t minus 13.3303. So this is the information that we gather. Of course, since there will be more and more omega values, we will end up in more and more things like this. So it's quite easy to depict it instead of writing it down or writing it to an array. So we can plot it. We have two things to plot. One of them is gain. So there will be a gain versus omega plot, and also the phase. So phase versus omega plot. Since they have omega in common, the x-axis can be chosen as omega, and they would be stacked vertically. So you can then be able to match the data from both plots. So that's basically what a Bode plot is, and that's also what we are going to do. By the way, as far as I remember, A10D should only give us the first quadrant. So A10 or A10D is just a first quadrant function. So there's A10-2D, which gives a better result as far as I remember. And A10-2D just expects, let me see, A10-2D, the value separately, so yx. So we should give it the imaginary value and the real value, so it can determine which quadrant it is and convert the angle data into 360 angle data. So it should not change anything as far as I am concerned. Yeah, it didn't change anything because it's not necessary for this, but it might be. So let's start from 1 to length of omega vec. Repeat this over and over again. Of course, now we need a vector for gain. And I can copy the size of omega vec and provide it to the zeros function in order to just make a copy of that with the same size and full of zeros. So size of omega vec get the size of omega vec, provide it to the zeros, so it will match the size of this, but it consists of zeros. I can repeat that for the phase. And this will go to gain ith element. This will be phase ith element. And I don't want to see immediate outputs. There we go. So gain, phase. Yeah, we should be good to go. Yeah, let's get rid of that. So if we look at gain and phase, there we go. Now, if I create a certain plot with subplot in order to stack vertical plots, so 2 rows, 1 column, the first one of that, hold on, grid on, and plot omega vec versus gain. So that's basically it. Let me increase the line width here. And that should be it. Now the second plot of this is versus phase. And that's basically it. Of course, we will see a plain line on both of the plots because we have only 2 points. So if we increase the omega vector here, for example, up to, let's say, 10, it will take quite some time to calculate this, and we get this result. Now, this is a jumping problem because it is a periodic function. If you think about A10, it has its asymptotes, and it seems like it's jumping here. We have to take the mod 180 and add 180. It was something like that in order to correct this jump. Let me maybe quickly try to do it, but I don't really remember. So phase, was it mod? Yeah, mod 4, 2. Okay. So what are the phase values? $118. So we're jumping from, first I'm going to fix this hopefully, from minus 180 to 180. So yeah, there's a 360 difference, but if we subtract 360 and mod it, we should somehow get it. Now, what happens if we mod it with 180? It shouldn't change, or does it change? I don't remember. So maybe adding to it 108, 360 maybe, then something like that. I don't quite remember it. There was a solution, but not quite sure about that. Yeah, 360, not 180. Well, I don't quite remember. Then minus 360, or first minus 360, then that. Yeah. But still there's some problem, I'd say. Maybe adding to it makes sense. I'm quite sure that this should be a negative value. So maybe yeah, this should be correct. For some reason, I have to add and then mod and then subtract back again because I want to realign these. There was a jump because of the discontinuity of the A10 trigonometric function, but yeah, you get the idea. Now, you might argue with the plot because it doesn't really look like a Bode plot. Is it really a Bode plot? Now, first of all, keep in mind that we would not like to have linear spacing here because in the frequency domain, there's high frequency, then also low frequency, and we want to combine them in the plot. So instead of using this, most of the time what we should use is the logarithmic spacing here. So for example, from 10 to the power of -2 to 10 to the power of 2 with, let's say, 150 sample points. Log space and lin space are two functions that can be used in order to create vectors. Since this is logarithmic spacing, what it does is it just lin spaces and then uses 10 to the power of lin space. As far as I remember it, it should be something like this. So the powers are linear spaced, but they will be used for the exponent, and you get the logarithmic spacing here. Whereas lin space is just taking the endpoint and starting point difference and divide it into the number of points, and you get the increment, and yeah, generates you that vector. So we have this omega vector here. Now, this has higher frequencies in it, but then it's still not there because, yeah, you cannot see that much of it. What you need to do is you need to have a little workaround here in order to show it logarithmically, because the values are logarithmic, but the plot shows only linear step. So what you have to do is you have to change the x scale of the plot to log. And the same for this one here. Once you have done that, it should resemble the Bode plot. And you can see now the spacing between the lines in the grid here did change because we're in the logarithmic scale. Now we have the Bode plot. Now, yeah. Let me also show you maybe an example where we can just apply an input and look if it's really the case. So if I am going to generate a time vector, for example, like that, let's say 10 seconds, and have a sine omega, let's pick a certain element out of there, let's say I equals 70. So I'm going to use the ith element for omega times t here, actually. Yeah, that should be the input. Let's create another figure here. Let's plot it to see if it's correct. There we go. So that's one plot, and the next plot is this. So let's say that this is the input of the system. And since we have GS defined here, I can use LSIM and give the system the input and the time vector in order to look what the output looks like. So size Y, you can see we have that, and it is this. Since we have calculated the output, what you can do is just provide the output here, and then maybe rerun the script here. So you can see we still have this sine wave here, but now we can look for the gain and phase that correspond to that plot. So we have I-70, so gain I and phase I should give us an idea. Now, the sine wave should have 0.21 as its peak value. Of course, here are the transients. I need a little bit more time. So it's almost there, but it needs a little bit more time. And it is almost becoming a cosine wave. So that's interesting. You can see that the sine wave, it does not really resemble one because it takes more and more time. We are in the transients. Even if you apply sine waves, you will have transients. So increasing it to 100 maybe would give you a better idea here. So this is basically it here. Now, if we click on this and there we go, we have 0.21. Of course, it's not really easy to show you that the face value is 84, but yeah, you have to calculate the difference, the time difference, etc., etc. But you would see that it should actually work. Now, do we have a better thing here? Maybe 10 to the power of -1. Well, this is not a very good system, therefore maybe we should change it. Let's add a little bit of, at least we should give it a gain of 3. So as we can see, the sine wave, the frequency here is 10 to the power. So maybe we should look at the first 10 elements of omega vec here. Well, I could use I equals 10 in order to demonstrate that the gain will not change that much. So you can see the gain didn't change, but since the frequency is low, we need more simulation time, etc., etc. But you can see that we are somewhere here, and there's almost no difference in phase and in gain, and you can verify that based on the plot. But you get hopefully the idea. The Bode plot can be used in order to examine a system. And the nice thing about the Bode plot is that you most of the time don't even need a model. If you have algorithms or design methods based on the frequency data, you're just good with a frequency plot. Now, this was the part 2 here. And you can see that we casually use the symbolic toolbox and the plotting functions, etc., in order to examine stuff in detail. Now, what about the last task, which is quite easier, but it's still important to mention, that what if we want to plot the impulse response, the step response, and ramp response of a certain transfer function? Let's quickly transition into that and then conclude our lesson for today. So let's again have the same transfer function. We like this transfer function. So let's actually, I can just directly get this one here because I don't really need the symbolic toolbox. We will do it just by using the control system toolbox. Of course, I have shown you already that you can use LSIM and generate all the functions as inputs that you want and get the output response. So LSIM is an option, but it is quite easy to get the impulse, step, ramp response, maybe also the parabolic input type of response, because they have a special meaning. So let me set up first my figure, clear figure, and then maybe subplot. Let's have 3 rows, 1 column, the first one of that. And there we go. Actually, the second one. Hold on, grid on. So I'm going to use the step function here. Step, and then GS, and then plot t, y, line width. And there we go. Maybe we should assign it a color. Let's say blue. And since this is basically a step function, since basically a step function is applied, what I can do is I can just generate the sort of step function. So it will have the same size as t vector, time vector, but I will generate a vector of ones. And that's basically it. Let's give it a black color here. And yeah, we should be good to go. So let's say x label time and maybe a little title, call it step. Yeah. There we go. We have created a plot, called it step, and we can see that we are immediately applying input 1, but the output takes some time in order to reach that value 1, and we call this part that we see here basically the transient of the system. So it takes quite some time in order to track step type inputs. This means that if I apply a certain, or if I change the reference, if I apply a step reference to a system, it will react in approximately 6 to 7 seconds. So if you open up your oven, it will take 6 or 7 seconds to heat the oven, which is actually practically pretty good in my opinion if it's an oven. But let's say you're pressing a button and it takes 6 seconds to reach a certain value. It depends on the application, but sometimes it's a good thing, sometimes it's not. It depends on the application. But here we can see that no system in nature can just jump from 0 to 1 instantly. It has a continuous path between the starting point and the point that is going to reach. So it's natural, basically. So what we are interested in is that we will apply an impulse input, and we want to see how we can just simulate that. Now, if we look close to the step function and its functionality, or what it is good for, is that we have to remember the Laplace transform again. We have to remember that step type inputs, if you like look at the Laplace table, are basically 1 divided by s, modeled with 1 divided by s. So yeah, and we have the system. Let's say we have GS. What y is it actually is equal to is GS divided by s, if you're looking at a step response. Now let's look for the impulse response. So what about the impulse response? So if we are looking for the impulse response, we would just apply 1 in the Laplace domain, not in the time domain. In the Laplace domain, the impulse function is actually just a scalar 1, and therefore the output should equal to be y equals gs. Now what I really want to do is I want to still use the same step function here, but I want to manipulate it so that I can get the impulse response, not the step response of a system. So yeah, in order to do that, let's assume that y tilde is equal to gs tilde divided by s, because this would be step gs tilde. So I want to find out what this gs should be equal to if I want to get the impulse response. Now you can see that yt is equal to gst divided by s, but what it should be equal to is basically gs. So I should propose a transfer function, a different one, and it should kind of act like the impulse response of gs. So therefore, I can see that gst should be equal to s times gs. So this means that if I copy this, and instead of using step gs, I want to use gst, or I should multiply gs with s. Why? Because if I pre-multiply it with s, the step function behind the scenes we'll divide it by s, they will cancel each other out, and it would be the inverse Laplace transform of GS, sort of. That's what I'm looking for. Now I didn't change anything. The only thing that I should change maybe is this function here. So yeah, this is the tricky part, but let me just do something cheesy here. Let's just subtract that. Let's make the zeros and add, just prepend it with 1 and hope that it should look like an impulse, because, well, the impulse function is actually just, the unit impulse function is actually 1 at time instance 0, and other than that it's 0. So I'm trying to emulate that. It's not correct, but I can get away with it, I guess. So let me just see if it runs. We messed up things. Dimensions. Oh, it should be a 1 by length. There we go. Now let's look at the figure, and we can see now, interestingly, that we apply just 1 at time instance 0 and then 0 for all the time. It kind of goes up and then down. It seems like an impulse response to me. Now, we would be more convinced if we can do the same for the ramp response, because ramp is more visible than an impulse response. So I am going to do the same, but this time around, instead of doing that, let me just get rid of it. This time around, if I'm looking at the at the ramp response, what I really want to have is, I want to have 1 divided by s squared as an input, and my output should be gs divided by s squared. Now, how can I emulate this with y tilde equals gs tilde divided by s? This is the question here. So if we equate them to each other, we will get gs divided by s squared, gst divided by s, multiply with s, this one goes, and voila. We have gs divided by s instead of gst. So this means that dividing by s or multiplying with 1 divided by s, which is the same, should give me the ramp response. Now, in order to regenerate that, the ramp response is quite easy. T comma t should give us a unit ramp. So there we go. Now let's first see the result. As you can see now, this looks like a ramp response. This is an impulse response. This is basically step response. And the reason why this works, or how we can use this, is basically the following. We have the step response. We have a certain system. We have input and output. Now, since this is an LTI system again, if I take the derivative of it, I'll get the derivative of output. Or if I take the integral, let's say integral dt, it will give us integral dt. So this is an interesting thing. Therefore, I know that the impulse is the derivative of step, and, well, step is the derivative of ramp. I can apply the same, or I can just include the derivative into the transfer function, so it turns into an impulse response, because I have used the derivative of the input, so the output will also be differentiated. Or the same goes for the integral. If I include an integrator to the input, that also will take the integral of the output. Therefore, I can use it for ramp responses. Of course, this is just to demonstrate to you that LTI systems have interesting properties, and sometimes we can exploit them like this, and we can just use the same step function over and over again in order to generate this impulse step ramp response. And the reason why we can also use parabolic, if you add one more, you can just also do that. So in order to work with that, we have to, of course, increase it to 4 just quickly and show you the result, that you can go on like that forever. So you can see we have this parabolic input but of course the parabolic input is quite getting out of control here. Whereas the system does not respond that fast. This might be relevant in some case, I don't know, but we can do it, so why not? So, well, we have toyed around with the control system toolbox, with the symbolic toolbox a little bit, in order to remember some basic aspects about the root locus, Bode graph, impulse, step, and ramp responses. This is more of a transitioning lecture for today, but from the next week on, we will be more control related, and we're just heating up these weeks for now.